right, the next presentation. From text to space, mapping abstract spatial models in LLMs during a navigation task. Please.
Okay. Hi, my name is Nicolás. I'm from the University of Buenos Aires. And today I'm going to be telling you a bit about how we map abstract spatial models in LLMs during navigation. So to start, sometimes we care about putting LLMs, embodying them in some kind of physical or virtual environment, for example, in robotics sometimes, or in virtual worlds. And this requires for LLMs to have some kind of inner representation of space, right? And if we're not using VLMs, then spatial information must be conveyed in textual form somehow. And there are many ways to do this. And it is not clear how to optimize the prompt for navigation performance. So many times in these applications, it is convenient to have small local models for these navigation tasks because they require, because these tasks require low latency responses and many times offline processing, right? So we ask if LLMs have an abstract representation of space inside of them. And first, we look at biological brains and to how they encode space. And it turns out that they encode space in an abstract way, which is independent of specific sensory input. So for example, here on the right, you can see a mouse that is exploring some space. And you can see the activation patterns of some neurons in the hippocampus. And you can see that, in fact, these are like representing some parts of space, which can be like specific patches or maybe the border of the space that the mouse is exploring. So maybe LLMs do not do this. Perhaps they are just shallowly responding to textual inputs and they are not encoding this space abstractly, which would be kind of like the stochastic parrot hypothesis. But if they do encode spatial information, we ask if they do this during navigation tasks and if they do it in an abstract way, right? So to answer this question, we created the grid world navigation, spatial navigation task, which is basically a basic 5x5 grid in which we placed an agent controlled by an LLM from the Llama 3 family of models from 1 billion parameters to 90 billion parameters. And we give this agent a starting position, and we also place a goal somewhere in this grid. And we give the LLM 4 possible actions, up, down, left, and right, and we provide them after each action with the updated world state over a maximum number of steps. So for example, here you can see in the left that the agent takes actually the optimal path and reaches the goal. This would be a correct trial. And in the right, you can see that the agent actually takes an incorrect path and does not reach the goal before the end of the trial. You might think that the task difficulty here is low because maybe we are not like placing any obstacles and there's only one goal. But this is because we're going to analyze the performance of small to medium models for which this task is actually challenging. Okay, so we represent, as I said before, space in textual form, right? And we actually create 3 different spatial information representation classes, which differ in the encoding framework, but convey the same information. So first, up here, you can see the Cartesian representation, which is basically where we give the model just the column and the row values for the agent and the goal, right? Then we also have topographic representations of space where the layout of the prompt is actually what conveys information about space. And finally, we have textual representations where we actually describe the state of the grid as prose. And to make sure the effects are due to encoding frameworks and not just to the superficial formatting of the prompt, we test 2 representations per class. And if inner representations of space are abstract, our thinking is that they should remain constant, right? The inner representations of the models should not vary when we change these representations in textual form. So we measure the success rate of the models, and here we're plotting it with respect to the model size, and also for each one of the 6 textual representations of space. And the first thing we can notice is that indeed success rate scales with model size for every representation type. But we see that Cartesian representations, which are the green ones, optimize performance, right? So you see that the green curves are indeed higher. And this effect is especially strong for mid-sized models. In this case, the 8 and 11 billion parameter models have a special boost of this success rate when you use Cartesian representations of space. Again, if inner representations of the models themselves of space are abstract, then they should remain constant when we change these representations. And so to test this, we took one of the medium-sized models, which is the 8 billion parameter model, and we probed it during decision making, and we looked for units inside the model whose activations were correlated with specific spatial features for all representation types, right? We cared about the units that were correlated with, for example, the agent's X position or the agent's Y position, or whether the agent was at the grid's border or not, for regardless of the textual representation that we were using. And indeed, we found that these units existed above chance level. Here we're plotting, for example, for the X position. We plot the number of significant units that we found. In black, it's the real number per layer, and in gray for the shuffled indices between representation types. So that's like the baseline, the random baseline. And we found that these units were indeed significantly above chance level, and mainly found in intermediate layers for the X position of the agent and for whether it was or not on the grid border. But the Y position was a bit different. It showed a different encoding, mostly in superficial layers, as you can see here, but it was still significant. And so next, we looked at whether units were also correlated with the decision outcome. So basically, we looked at whether the action takes the agent closer to the goal or if it doesn't. And we looked for units that were correlated with this information. And our thinking was that an encoding of action correctness requires an understanding of spatial relations in space, for example, the relationship between the agent's position and the goal position, and maybe of task objective. And we indeed find again that abstract units encoding this for all representation types exist way above chance levels, as you can see here, and again are localized in intermediate and deep layers. Finally, we thought that if LLMs have an internal system of spatial reasoning, then this system should be more active anytime spatial reasoning is required, and not only for navigation tasks. And to explore this, we created a data set of questions, half of which were spatial in nature, and we probed the LLM right before the answer. And we found that the units that we previously found that were correlated with action correctness during navigation tasks were also more active during these spatial questions than during the non-spatial questions. But crucially, when we went back to the navigation tasks and we performed ablation experiments with these units, this did not impair performance. And so what conclusions can we take from this work? First of all, how we encode spatial information in the prompt matters. If you're doing something like this, whenever possible, you should try to use Cartesian encodings of space. Model scale matters as well, but smallish models can perform relatively well if prompted in Cartesian terms. Of course, many questions remain. How do other families of models behave? We only tested Llama 3. Do larger models show these spatial representations as well, and how do these change for harder tasks? And finally, ablation experiments do not negate the presence of abstraction because we did find these units that represented spatial features regardless of how it was represented. But they do show that abstract units cannot be the whole story, right? So we can ask, what would a more complete picture of spatial processing system look like in LLMs? And also, how would it change for VLMs, right? So that's it. You can scan the QR codes for the paper and for the code on GitHub. And if you'd like to know a bit more about our work in agentic systems, you can scan the third one, which is a framework to build scalable and robust multi-agent systems. And you can email me for questions or collaborations or anything. Thank you.
Thank you very much. Questions? Yes?
Hi. Thanks a lot for the great talk. You had my question on your future research, so I would love to ask, like, how do you think other model families behave? But do you have a hypothesis on how the training data would change this behavior for other families?
Yeah, so like it's clear that these language models are not specifically trained to navigate space. So it's already kind of surprising that they are able to do this at all, right? And it is also surprising that they have some abstract representations of space. So like my hypothesis would be that if you actually were to train these models, for example, fine-tuning them to actually navigate space, I would argue that the representations would probably get stronger. Like if, for example, if we see here, like in the thousands and thousands of units in the model, we found a few hundred in total that are representing space robustly and abstractly. So it's likely that if you actually were to fine-tune the model to represent this space and to navigate it, this would get stronger, you know? Yeah.
Thank you.
Yo.
Thank you. Any other question? No? Yes.
Thank you for the great talk. I have two questions. First, can you elaborate a bit about the grid choice, like the sizes of this grids and more about the setup?
Yes, of course. So I'm actually showing you just one of the tests that we did, right? So we tested different grid sizes. For the model sizes that we used, we found, like, if we go back to the success rate, we find that this particular grid size gives us like a good baseline where the smaller models are performing near baseline and the bigger models that we tested are basically solving the task, right? So this is like a good trade-off here in the size of the grid, but of course we tested smaller and larger grids, and what you would expect happens, which is that the task can become easier and harder. We also tested obstacles in the grid and multiple goals. And again, like you can make this task harder, but then you need larger models and it becomes harder, for example, to program. Yeah.
As well for the second question, for the layer where you show like the most activation, have you tried to like intervene on this layer or like probe it for like activating it the whole time or something like that?
Yeah, what we tried there was the ablation experiments, right? We tried first ablating all of the units that encode space abstractly, some of the spatial features, and we find that there is like no effect when we do that. And when we do it like for specific layers, for example, there are basically two cases. One case where you don't have an effect if you don't ablate like enough units, and when you reach some threshold, you basically lose all behavior, but the model just becomes incoherent, right? So it's not even able to output coherent actions. It can't tell you down, left, right, up. Like it's not able to output coherent text. So our hypothesis there is that these representations are like widely distributed throughout the network, and so when you ablate those units, you're not only interfering with with this specific spatial representation, but you're actually interfering with the whole of the model, so you cannot actually get coherent behavior. Yeah.
Okay, thank you.
Okay, thank you.
All right, thank you very much. One more time, please. So this is the last presentation of the conference. And I hope